Alright, this is the second video on section 16.8, which is about Stokes Theorem. Let's remember what we did in the previous video. So Stokes Theorem says something like this. Given the vector field on R3, and you want to compute the line integral over a closed curve, and then that is written as the surface integral of the curl of f over the surface S. But how are those two related, S and C? Well, it's related in this way, namely the curve C is the boundary of the surface S. And then both of them are oriented, and the orientations are related as induced orientation. Namely, if your surface looks like this with upward orientation, then the boundary is, in this case, the bottom part here. And the induced orientation is determined by the right-hand rule. So your thumb corresponds to orientation for the surface. So in this case, thumb up. And then the fingers correspond to the orientation for the curve. So in this case, you have a thumb up and your fingers are wrapping around the thumb in this direction. So this is, so to speak, the counterclockwise direction if you view from the above. And then if the orientation of the surface is the other way around, the induced orientation is the other way around. Okay, then basically there are two different ways of using Stokes theorem, namely to compute the surface integral of this form, you can reduce it to the line integral, so namely in this direction. Or sometimes you could actually do the other way around, namely to compute the line integral of a vector field in R3, you could use Stokes theorem and then compute it by computing the surface integral. And the last time I did this direction, and in this video I'm going to work at an example where we use Stokes theorem in this direction. Like this example. Evaluate line integral over the closed curve dot dr, where the vector field f, which is with three variables x, y, z, is given by negative y squared x z squared. Okay. And C, the curve C, is the intersection of x squared plus y squared is equal to 1, and y plus z is equal to 2. Okay. What is this? Well, this one is circle with radius 1 on the xy plane, but in the xyz space, this is a cylinder going up in the direction of z-axis. And then this one on the yz plane, it's just a line. Like this. 2, 2. But on the xyz space, since you don't see any x here, this is parallel to the x-axis. So you can just stretch this line parallelly in the direction of x-axis and you get a plane. And then indeed, if you combine those, the intersection of those two is something like this. Let me write down a picture. So it's a cylinder. First we have a cylinder. And then you cut the cylinder. So intersection of the cylinder and the plane is obtained by cutting the cylinder with a plane with some angle like this. So it looks like this. like this. And our C is this part. This is our C, the intersection of the cylinder and the plane. So this is cylinder is x squared plus y squared is equal to 1. So cylinder with radius 1. And then top piece, this cap here is y plus z is equal to 2. And we need to specify the orientation. So assume that C has a counterclockwise orientation. Viewed from above. Meaning that the orientation of C is this way. Okay. Then, by Stokes theorem, here's what it is. We choose our surface S. So if you want to use, let's go back to this. If you want to use Stokes theorem in this direction, in a way, you could choose any surface you like as long as the surface has C as its boundary. So in this case, let's choose as our S this plane. So this is our S. S is a plane with the boundary like circle. It's not really a circle, it's indeed an ellipse, but it's like this. Okay, then by Stokes theorem, we have this. The line integral we want to compute is computed as a curl of f dot ds. Okay, so that's Stokes theorem. Let me just put it in by Stokes. So now here's the answer. So, like I said, choose our surface S so that the boundary of S is C. And like I said, as long as the boundary of S is C, you could choose any S you like, any surface you like. So in this case, so let's just choose S to be the disk on y plus z is equal to 2, namely it's the disk on the plane cut by the cylinder. So the shaded piece is our S. Okay, then we have to specify the orientation on S in such a way that the orientation induces the given orientation of the curve by the right-hand rule. So that means in order to get this orientation on the boundary, the orientation of S has to be upward by the right-hand rule. So we choose upward orientation. So we choose S to be the disk on this with upward orientation. Then by Stokes theorem, the given line integral is surface integral of curl of f dot ds. So now we have to compute the curl of f. Remember how to compute the curl of f? I'm not going to work out the calculation, but it turns out that curl of f, which is computed by this way, and that is computed as let me just write it down. This partial x, partial y, partial z, and negative y squared x z squared. And then if you work this out, you are supposed to get 0, 0, 1 plus 2y. That's what you're supposed to get. Okay, so after all, what you have to calculate is this surface integral over S where the integrand is this. Or if you like, you may write it as surface integral of 0, 0, 1 plus 2y dot ds. Okay. You want to integrate this vector field over S, where S is just, indeed S is just a plane, but it's a portion of the plane. Yes, okay. So then now we have to compute the surface integral of a vector field. And remember, there are 3 steps to do it. Step number 1, you just parameterize our surface S. How? Well, namely, we have to find RUV. But in this case, the surface we are looking at is y plus z is equal to 2. Our surface is y plus z is equal to 2. And of course, this is written as z is equal to 2 minus y. So that means our surface S is z is equal to something. That something is in terms of x and y. Indeed, you have only y. So for this case, there's a canonical way of parameterizing. Namely, we have r of xy. So instead of r of uv, we just use r of xy. Well, if you like, you just say u is x and v is y. And then this is x component is x is x, and y is y. And z is this, 2 minus y. Okay. All right. Yes. Then we have to find the domain of integration, the region of integration. Well, in this case, that means just look at the picture. In order to create this surface upstairs, you have to find the region where x and y have to move around. And in this case, x and y just move around downstairs, namely that's the disk with radius 1 on the xy plane. So in this case, our region D is the set of all xy. Remember the set notation such that x squared plus y squared is less than 1, meaning that we have on the xy plane, we have disk with radius 1. And then by R, we get this disk on the xy plane gets mapped to this portion of the surface here we are looking at here, xyz. And then this disk floating in the air is on the plane, or this one, z is equal to 2 minus y. So that's the picture. All right, that's step 1. And of course, you don't really have to write this down. Maybe you want to write this down, but anyhow, step 2. Compute Rx, Ry, and check the orientation. So let's compute this one. So remember how to compute it. This one is, it's a cross product I, j, k, and then you list the derivative of this with x, so you get 1, 0, 0 in this case. And here you list the derivatives of those coefficients with y, so it's 0, 1, negative 1. And that is equal to j plus k. And that's 0, 1, 1. Okay, and then now check the orientation. Namely, check if this one gives the right orientation or not. And the orientation for our surface is upward orientation, like going this way, upward orientation. So that means if you look at the picture on the YZ plane, it looks like this, and then the given orientation is this way. So this line is z is equal to 2 minus y. And then this vector is precisely the vector going this way, right? Forget about x on the yz plane, and it's just vector 1, 1. And vector 1, 1 is vector going this way. So it's indeed that gives the same orientation. So this is upward orientation. So therefore, it's a correct orientation. So the upshot is, therefore, r of x cross r of y is the correct orientation. Okay, so we could use this to calculate the surface integral. And then finally, step 3, plug in everything to the formula. Plug in to the formula for the surface integral, namely the given surface integral s 0, 0, 1 plus 2y dot ds. That is double integral over d, and then our f. But in this case, we already have, we don't see any z here. So this is our f. And then that's the same as f of r of x, y, z. Just coincidentally, it just happens in this case that if you plug in the parameterization, you get the same thing, right? So the integrand is this. We integrate this vector field, and then you plug in our parameterization here to here. That means x becomes x, y becomes y, and z here should become this, but we don't see any z here. So just that's it. So we don't really have to do anything. Dot and this one, the vector that gives the orientation 0, 0, 1. So this one is what this one is. xr cross xy and then dx dy. And so therefore this is equal to d and 1 plus 2y dx dy. Where our d is, like I said, this guy. This is our d. Disk with radius 1. With radius 1. So to do this, to compute this, what should we do? What should we do? Well, it's double integral over the disk. So we can say x is equal to r cosine theta y is equal to r sine theta by using the polar coordinates, sine theta. And then if you do it, dx dy becomes r dr d theta. And then r is between 0 and 1 because it's radius 1. And then since it's the entire disk, theta is between 0 and 2 pi. Okay, if you do this by using, so here, by using polar coordinates, and then if you do the calculation, you are supposed to get pi. So the answer is pi. All right, so this is the end of this video, and which is the end of this section on Stokes theorem.